in order to understand how carbohydrates are cyclized to form monosaccharides, we must recognize that when we represent in the notebook or on the blackboard a molecule, for example, glucose, as is the one that is represented at this moment and I represent it vertically or horizontally, that the chain in reality is not in this completely vertical or horizontal format because of the bonds that exist between the carbons and their hybridization. Actually, if I could see a molecule of glucose, I would see that it forms more of a horseshoe more than a horizontal vertical line, and that horseshoe has carbon 1 at one end and carbon 5 at the close end. Therefore it will be very easy or very simple for these carbons to join together to form the ring. So it is the real arrangement, although we are going to work with the vertical arrangement. Having said that, let's consider the glucose molecule. Let's consider, as we just said, that it would be like a horseshoe, where here I have carbon 1 and here carbon 5 close to each other. If we analyze carbon 1, it has an sp2 hybridization with a double bond with the oxygen of these two bonds. There is one that is the pi, which is weaker than the sigma. And we also have two pairs of non-bonding electrons that indicate to me the high polarization of that bond, and on the other hand carbon 5 contains the hydroxide group where oxygen has a negative charge density, that is, it is a negative dipole and hydrogen is a positive dipole due to electronegativity. Because of this then, and carbon A is very close to carbon 5, which what is going to happen is that the hydrogen of the hydroxide group of carbon 5 migrates and joins the oxygen of carbon 1. The pi bond is broken, which means that now the carbon is left with a free valencia, and that free valencia of the carbon is going to join the oxo of the carbon 5, which I repeat are very close because in reality they are a horseshoe as an intermediate structure before going to the cyclization to the form it has. I am going to represent this migration of atoms and this formation of new bonds in the following way. I am going to represent the 5 6 carbons are 2, 3, 4, 5. 6 carbon 6 is going to be outside the formation of the ring, the carbon A. Now I am left with an O group that was not previously there, which is the one that is formed when the hydrogen migrates towards the oxygen, a bond to the hydrogen that it previously had and a bond to the oxygen that we are now going to finish when we get to carbon 5, carbon 2 and unaltered carbon 3, unaltered carbon 4, unaltered and carbon 5 with a hydrogen to the left and a bond to oxygen that joins the carbon 5 with carbon 1. So the bonds that the carbons that are forming this cycle are carbon 1, carbon 2, carbon Tr, carbon 4 and carbon 5. If we consider how many elements or atoms form this cycle, are 1 2 3 4 5 6 atoms form this ring to this cycle, and since they form 6 atoms it will form a hexagonal base structure where 5 of those bonds, 5 of those vertices are going to be carbons and 1 is going to be oxygen. So I am going to Represent a structure. Hexagonal, where one of the vertices is oxygen, and to go from the linear structure to the hexagonal structure, all the O that are on the right in the open chain structure are represented downwards in the closed or cyclic chain structure, and everything that all the O that are on the left are facing up. Therefore carbon 1 is going to have a hydroxide group down, because here it is on the right, and a hydrogen group, a hydrogen atom up. Carbon 2 is also going to have a O down and a hydrogen up. Carbon 3 has the hydroxide group on the left, so I put it up and the hydrogen down. Carbon 4 is going to have the O down because it is on the right hydrogen up, and the carbon 5 is going to have the group of CH2O of MiIC carbon 6 and a hydrogen. I am going to number them, and it is 1, 2, 3, 4, 5, 6, so that this structure is not so cumbersome. It is simplified as follows. I draw the 6-sided ring, and I go to draw only the groups O, but I'm not going to write the word O, but I'm just going to put a dash where each hydroxide group is found. Therefore carbon 1, the hydroxide group, it's down, I draw it down. Carbon 2, the group hydroxide, it is downwards, drawing downwards. Carbon 3, the hydroxide group, it is upwards, drawing upwards. Carbon 4, a tetrahydroxide group, downwards. Carbon 5, I am going to write the terminal group and renumber. This is carbon 1, 2, 3, 4, 5, 6, so then it represents the molecule of cyclized glucose 2. Name them. I will say that it is D because it comes from glucose D, which is the one with the O of the penultimate carbon, that is 2. Say from the last chiral carbon on the right, I will say that it is gluco because it comes from glucose. I go to put a pyranose ending on it because the cyclized structure is reminiscent of the structure of pyrano, which is this one, so that's why it is called pyranose. I'm going to also add the following. If the O of carbon 1, that is, the one that is formed new, was to the right, then it I call alpha, so this is the alpha of glucopyranose. If when this O is cycled, it is actually in reverse. In an inverse situation, the only thing that will change is the position of this O, and I will then have a very similar molecule, with the only difference being that the first H was facing up in the hexagonal representation, and this last glucose, instead of being called alpha, is called beta. So this is the beta of gluco pyranose, and I remind you that alpha comes from the position of the first H of which was formed. It is downwards, and beta indicates that the O of carbon 1, which is called anomeric carbon, it is upwards.